exploration here in the session, and so I'm not going to talk about how we use quantum mechanics, as most of you are doing, but I'm going to talk about how to test it, because Shimon gave a very good introduction. Turned out that my first few slides are actually identical. The motivations, like why we know that quantum mechanics must be wrong, or the standard model must be wrong at some point, right? So why would we look for new physics? And it's actually the same list that Shimon just showed. Most of the stuff, the universe, even the same graph, is kind of unknown. But this is not complete, right? So there's other things that could be added, like neutrino oscillations and things like this. So we know at some point it must fail. And there's different strategies to look for this, and this is also what Shimon just kind of summarized. So there's different frontiers where we expect, or where we like to look for, which is the energy frontier, so bigger and bigger accelerators. And then there's the sensitivity frontier. So if you look for rare events, like things that should not be there, like the proton decay or things like that, so you need to be very sensitive. Why? Well, because if these things were not rare, they would have been already detected, right? But we are at the precision frontier, so we want to just look for tiny, tiny deviations. And if you look into history of physics, when there was a big revolution of physics, it was kind of always this kind of thing here, right? So that there were deviations between, or discrepancies between experiment and theory. Okay. So I already said this, and yeah, so we're working on atomic hydrogen, and one reason is, well, because it's the essential element. The other reason is that all modern field theories are actually rooted on QED, quantum electrodynamics, and the best system for QED is hydrogen or hydrogen-like systems, because they can be calculated with the utmost precision. Why do we need to calculate them? Okay, it's back again. Well, because we are doing fundamental science. So we don't have an application in mind. We don't want to build something. We're not engineers. We want to test physics. And how do you test physics? Well, there's 3 parts, or maybe there's 4, or maybe 5. So first, well, we have a theory, we have an experiment, and then we compare the two, right? And see if it agrees or not. If it doesn't, then it gives us a hint how to refine things normally, yeah? Or completely revise it, but normally things are getting defined. But typically what happens is that if we are not happy with number 3, and then we need more data, right? So if I have time, I will also speak a little bit about this. And then if I have even more time, I will maybe also speak about a future project that we have just started in our lab. Okay, so let's go through the theory. Let me walk through the history of the hydrogen theory of the last 100 years in, say, just 1 minute. Because I guess most of the stuff you know from kindergarten already, so we can be quick on this. So these are the people that have been developing. So there was first Balmer kind of empirically explained the spectrum of hydrogen without any explanation, and he came up with a famous Balmer formula. And then Bohr was probably the first kind of semi-explanation. He just started he kind of started out with a Keplerian sort of system, but then demanded that the circumference is just an integer multiple of the de Broglie wavelength, which is kind of not exactly what he said, because the de Broglie wavelength was actually discovered a couple of years later than Bohr, so he was a bit ahead of time. But so it was kind of clear there was a wave, but there wasn't a wave equation. This is what Schrödinger came up with, and here you see this bubble sort of thing. This is how we described the wave function of the hydrogen atom. And then this was not relativistic, and there's interesting problems how to make this relativistic, and then finally Dirac figured it out, and there's this fine structure constant that showed up. That is kind of the speed of light of the electron in the ground state in atomic units. That's one way to look at the fine structure constant, and there's all this vacuum stuff that comes in, it's because this is not in the Dirac, not really in the Dirac theory. The electronic vacuum and the photonic vacuum, they change the energy levels slightly, and you have to take it into account if you want to be really, really precise. So this is how it looks like in formulas, right? I hope you all know this term here. So normally there's a Rydberg constant here, so I wrote this down in here. In atomic units, 1/n² is the principal quantum number. And this is what comes out from the Bohr and the Schrödinger theory. So they give the same prediction here. And as I said, this is not relativistic. Okay, not relativistically correct. And then if we throw in Dirac and solve this, we get something more complicated, right? So this is not like your homework assignment or something like this. If you get the right answer, it's normally simple. Unfortunately, nature seems to work the other way around, right? So the more correct answer is more complicated, unfortunately. And if you have something like this, there's additional quantum numbers. It's the total angular momentum of the electron here. And then there's the fine structure constant. It shows up for the first time, of course, because it's relativistic. It should show up here. And first thing you should do is like, well, if you see this, there's also the principal quantum number. You type this into Mathematica and say expand, right? And it's nice to see that the leading term is the Bohr term, of course. Otherwise, it would be really off because the Bohr already had some good predictability. And you can also see that the relative magnitude of this relativistic correction is alpha being 1 over 137 is roughly 10 to minus 4, right? So if you measure only the first 3 digits, you would conclude you cannot test relativity, let's put it this way. So you have to add more digits to test for more physics ingredients. And there's more than this. So first there's the recoil correction, which is due to the finite mass of the proton. So this electron-proton mass ratio, you see this factor goes to 1. If you put the proton mass to infinity, and this factor goes to 0, right? So it recovers the old, or the infinitely heavy nucleus description. And the thing is with relativity, it's like roughly speaking, you have the nucleus and the electron going around the common center of mass. They have different eigentimes, which means you cannot simply replace the electron mass with a reduced mass, as you would do with the Schrödinger equation, to take into account for all the recoil corrections. And turns out there's an infinite number of recoil corrections, okay? And there's more stuff. There's all the vacuum stuff. So there's self-energy, vacuum polarization, 2 photons, 3 photon corrections, radiative recoil, and so on. So this is the knowledge that we have at the moment. These are all the terms that are known, okay? So it's up to date, not exactly up to date, almost up to date. And there's a lot of terms. It's not complicated, it's just confusing, right? To use it as an experimentalist. And there's different terms that have different meanings. So this thing here, the proton, that takes into account the finite size of the proton in terms of the proton charge radius. We have taken into account the finite mass. This takes into account the finite size. And that is a small term, is actually one of the smallest, but it's the most annoying, right? Because it has the largest uncertainty. We're talking about uncertainties, not just about the size of the terms. If we just write this in a more compact form, this is typically how we write this. So we have the Bohr term, we separate it out because we like it, then we have all the QED corrections, and normally it includes this charge radius correction. Again, it's small, but I separated out because, as I'll explain to you, this is really annoying. This is a really annoying term, right? It's small but annoying. So if you want to read about the theory, this is updated in code data, like every couple of years. They add in more terms, and then you have to retype the Mathematica code that I used for making the slides, by the way. Okay, and then there's another thing that I put in, is the Rydberg constant here. The Rydberg constant multiplies the generic theory expression. The theory expression has to be unitless. It's like, if you think about it, if you ever get a result from your theory that has a unit, there must be a measurement going into this somehow, right? So theory can only produce numbers. And by the way, measurement can also only produce numbers because we always measure relative to a unit. That's a number. But we have to convert to the right units. And the Rydberg constant, if you like, is a converter to SI units because we measure in SI units. So we need this thing here. Okay, so that's the theory. That's not what we're doing. It's just to summarize. We do experiments. And one of the important experiments is, we run 2 hydrogen spectrometers. And this one here, that can measure the 1s to 2s transition. The 2s level lives long, like a second, because there's no 1p state, right? So it cannot decay via dipole transition. So that's kind of the gold standard for us. The 1s, 2s it doesn't have the Q of 10 to the 18, but it's 10 to the 15, yeah? So this is our clock transition, if you want. All other lines are broader than this. And the nice thing about the 1s to 2s is you cannot excite it with 1 photon, but you have to use 2 photons. And that takes out the Doppler shift because, as I might be able to tell you, atomic hydrogen is a beast when it comes to laser cooling. So it has not really been achieved. Yeah? So there's, under other conditions that we don't like, it has been achieved, but it's very difficult because of the cooling laser that is required would be 121 nanometers. People that work with lasers know that this is kind of impossible, right? So we use an effusive beam that comes out from a cryogenic nozzle at 5 Kelvin. They're still 300 meters per second fast, these atoms. So in useful units, that's 10 to the minus 6 times the speed of light. and the Doppler shift would be 10 to minus 6 in relative units, so that gives us only 6 digits, and if we model it, maybe we get 2 more, right, if we know what these Doppler shifts are. But we excite these atoms with 2 photons, so there's a standing wave here. The atoms travel along and they absorb a photon from the front and one from the back, and one is positively Doppler shifted and the other one is negatively Doppler shifted. It adds to 0. That's a nice feature of this kind of spectroscopy, right? And then we measure the frequency with an atomic clock and the frequency column. Okay, so what's the next in this business, right? If you killed the largest systematics, it's like Shimon just said it, right? The next question obviously is what's still limiting, right? So in this case, there's several things, and one of them that I would like to talk a little bit is the second order Doppler shift, which is time dilation. These atoms fly through our apparatus 300 meters per second, and they experience a time dilation, and that is proportional to V over C squared, which is 10 to minus 12, or there's a factor of 1/2 in front, so 5 times 10 to minus 13, and we can model with at a percent level, we get to like 5 times 10 to minus 15. This is kind of what we can do. And one trick to do this is like we look at our line. As you can see, this is asymmetric. It's the Doppler shift that's folded in, and because it's with velocity squared, it shifts only to the red, not to the blue. So this is kind of the line-shaped distortions that you don't like. You like to have symmetric distortions. You fit any symmetric line to it, you get the right answer, even though the fit doesn't matter. But if it's asymmetric, then it's a problem. So what we do is like we use a delay to detect the fluorescence from our atoms. And if we just wait longer, then more and more of the fast atoms are already gone, and we only look at the slow ones. Of course, that reduces our signal, but as we increase that delay, the line becomes more and more Lorentzian. And this is kind of what we do to find this transition frequency. And we have been doing this for quite some time ago, because I'll come back to this, why it's not worthwhile to improve this. We know how to improve it, but there's no physics case for that. And this is the result that we have. This is the 10 hertz uncertainty in 2,466 terahertz. That's the clock transition frequency, or 5 times 10 to the minus 15 in relative units. Okay, so now I've explained the theory and one of the experiments. Okay, we have several, and we want to do a comparison. Okay, so to test QED. How do we do that? So we have this equation that gives us the energy levels, and differences gives us the transition frequencies, of course, and we want to compare this. And now there is parameters in this thing, right? That's the nasty thing. Yeah. But how many parameters are there? And then you can start counting, and then you might realize that other people might be able to measure the fine structure constant, the electron to proton mass ratio, and so on, with other experiments more sensitive than we can do that. So we can use their result to plug this in. But there's 2 things that we cannot be used from something else. Clearly not the Ripper constant and the charge radius. The charge radius, we can argue if there's other experiments that can do that. We think not. Other people think we could. But for the Ripper constant, there's no question. So we have 2 adjustable parameters. Now, if we measure only one transition frequency, we can always find actually an infinite number of different combinations of these parameters to just match our measurements, right? So that's a problem. So we need 2 transitions, at least 2, to determine these parameters. And then we haven't tested anything, because we have 2 adjustable parameters. We can adjust to our 2 measurements, and any theory that you give me would work. That has just 2 parameters. So parameters kind of express our ignorance, and here's an example, an old example from nuclear physics. Doesn't really matter what this means, but if you have enough parameters, you can make a nice fit, right? And if you have even more parameters, you can even make theory predictions, right? So these parameters are a problem, as you can see. Here's another way of looking at it. So this is the space of the 2 parameters, the Ripper constant and the charge radius. And this gives us a probability distribution where these constants are lying, using the 1s, 2s transition frequency, right? So brighter regions mean higher probability, black means it's unlikely, right? But you can see that you can find an infinite number of different combinations here. So we need something else. What is that? There's many different transition frequencies. One is very powerful, besides the 1s, 2s, and that is the Lamb shift, which is the 2s to 2p transition frequency in muonic hydrogen. So what's muonic hydrogen? You take a hydrogen atom, you throw out the electron, you replace it by a muon, and then your energy levels get much more sensitive to the charge radius, because the Bohr radius reduces by the mass ratio, which is roughly 200. And so the overlap of the wave function increases by 200 cubed, right? So you get something like 7 orders of magnitude enhancement. So this term is no longer small, it blows up by this term here, okay? And so this has been done, And so it has very high sensitivity to the charge radius, this measurement, but almost zero sensitivity to the Ripper constant. And if you plot this in here, it looks like that. Okay, so nice, it's two lines, they meet, right? No surprise. And so that, at least with this, we can just find, reliable values for these two parameters. But we haven't tested QED, right? So if we want to test it, we need more data, right? And one way to do this is to go to higher states. And 1s to 2s, I told you, is very narrow band. And the problem with this is that as you go higher, the lifetimes get shorter and shorter. The natural line length, the 3s is already megahertz wide. And if you go even higher, then it gets like 13 megahertz and so on. They get narrow again at the Rydberg states, but we don't really like them because they are so sensitive to everything. So this, we thought, that would be a good way to test it, also because this is a wavelength that we already have. It's 486 nanometers, and because of this 1/n² scaling, there's small integer ratios between these wavelengths and hydrogen, and we could just make another laser like this. It's very close to this one, and just cross it with this beam, and now we're using that old apparatus as a source of cold 2s atoms to excite from the 2s to the 2p. Okay, so we did that a couple of years ago, and then we find this, right? So it sort of agrees, right, within the standard deviation, and so we can look at that as a test. So a test of a theory is, to summarize that, so you have a theory with parameters built in. You make more measurements than you have parameters. It's overdetermined, and then you check if the parameters are consistent. We don't care about the values, we care about consistency. That is the test, right? So, and you see, it's kind of fulfilled. More recently, we went on to the 2s6p, and we improved a lot of things, and we got our error much further down. And this is what you can see is they nicely meet in one point. So if you only take our data from our lab, it looks like that QED is not invalid. Yeah. And so we also went on with this by probing another transition. This actually is a 2-photon transition. For the 1s to 3s, we use a frequency comb to directly excite it, maybe in the interest of time, maybe very quickly. So we use a mode lock laser. We frequency double it twice, get 205 nanometer laser pulses that are then colliding in an enhancement cavity. And the point where they collide, the atom sees traveling pulses from both sides is Doppler-free, and we get the Doppler-free excitation in here. Okay, so this is kind of the spectrum that we see. It's like all folded in with a frequency comb, and there's several fine structure and hyperfine components. And we actually like this one here. That's the narrow one. It's this one that peaks out in the center. If we throw this into this graph, it looks like this. Nice. Again, it hits right on in the center. There is another group that are working on this. Maybe there's 2 more groups in the world. There's not so many people working on this. So our colleagues in Paris, the group of François Birabin and François Ney, they also measured this 1s/3s transition frequency, and this is what they got. Okay, and so here you might think, well, okay, QED is wrong. Okay, something fails, but unfortunately. This is not so, right? Because these are 2 lines at 1s/3s, they should agree no matter what the theory says, right? So that points to an experimental problem, right? Either in Paris or in Garching or both, and we still haven't figured out what this is. So not sure if I'm doing, maybe I have a few more minutes, to tell you a little bit about a project that we have started to build. And that maybe nicely connects also to Shimon's work, because we think that we might be able to build a hydrogen clock. A clock not with some strontium or ytterbium or some other ions, but to use hydrogen. Okay, so if you look at it, the level scheme of hydrogen is actually not so unsuitable for a clock, because it has a nice clock transition. It's narrow. Well, it's not 10 to minus 18 Q, but 10 to minus 15 is not so bad. And then we have a cooling transition, which is kind of strong, like 100 megahertz line width. So you can, if you saturate it, you just get 100 million photons per second, which is good. But the problem is this wavelength. Right? If you're an experimentalist, you would say, well, okay, forget it. You will never be able to order this from Toptica, at least, or from somebody else, at least not anytime soon. And then also, there is, so the laser cooling is a problem, and even if you had this laser, there would be more problems because there's a huge photon recoil shift in this. You know, typical recoil velocities, when the atom absorbs a photon, it recoils and moves on. Like in rubidium, I think it's like two orders of magnitude smaller, right? Typically. This is because the photon is really big and the atom is really light, right? So both of them add to this recoil. And so also it means that the Doppler limit for cooling is fairly high, right? In normal atoms is microkelvin, and here it's millikelvins, and then you go to, you know, sub-Doppler limits like the recoil limit, and also the recoil limit is very large. It's because of the large recoil. So even if we had laser cooling, it wouldn't be very effective, okay? And so it's all because of this huge recoil. So now we wanted to make that, you know, disadvantage of the large recoil, we want to, you know, turn it into an advantage, right? So how do we do that? Well, we take this thumb down here, right, and just, it's easy, right? Just turn it around, and, well, just a joke, okay. So we think that we can, trap atomic hydrogen, and the important thing is that how do we load the trap? How do we load the trap? The trap itself isn't a problem, as it turns out, but we need to get the atoms into the trap, and if the trap is a conservative potential, right, if you don't remove the momentum while you're inside the trap, it will just, as it rolls in, it will roll out, right? Okay, and the other thing is, like, since we are using a Doppler-free two-photon transition for the clock transition, we don't even have to be cold. We just need to have it in the trap to, you know, interrogate it long enough. Okay, so the idea is to use you know, an optical dipole trap, and Shimon just explained to you what the magic wavelength is. It's just the wavelength where the excited state and the ground state of the clock transition have experienced the same AC Stark shift. You can use it for trapping, but it doesn't affect the transition frequency. And this happens to occur at 550 nanometer, which is a very nice wavelength, just a double frequency yak. You get tons of power, narrow line with everything. So the trap isn't the problem. Now what we want to do is we want to generate a 2s atom beam that is slow, right? Kind of not in this community slow, but kind of for us slow. It's 5 meters per second. For us, it's already slow. And then if such an atom rolls into this trap, there's a high probability that it will quench because there's a perturbation of the trapping laser. And when it quenches, it gets a recoil. And if the recoil goes in the right direction, you know, this almost stops the atom inside the trap. So this, we think, could be a cool loading mechanism. And actually, they quench only at the point where they should quench, not outside. It would be useless. Only at the point where they should be quenched. Okay, so how do we make a 5 meter per second atomic beam? And what we are setting up at the moment is we just, again, use the 1s to 2s transition, but in this case, we don't use the Doppler-free component. It doesn't get a recoil because it gets 2 photons from either side. But there's the same matrix element absorbing 2 photons from either side, and that gives a huge recoil. And again, we make use of that large recoil. So that really disperses, and that's actually drawn to scale. So if we separate out the 5 meters per second, that should deflect by 33 degrees. So that's a large angle. So that's kind of what we want to do. And now, why is this interesting? Well, we could make another clock that is computable. So we can make a computable SI second because this thing here is computable. This is the clock transition. And to make use of that, we would define yet another constant, which would be the Rydberg constant. Okay, so that's far in the future maybe. But why is that interesting? Well, maybe very quickly, there's 3 ways to define units. You can take an object, an artifact, or a natural, like a cesium atom, or you can define some constants with dimensions. And it turns out that this is the very best way to do this for several reasons, to define constants. And maybe click over this quickly and show the graph that also Shimon had stolen from Wikipedia, I guess, right? So if you look at the current SI system, it's all based on defined constants. So the Planck constant is defined. Well, the mole we don't really take seriously, right? The candela, well, come on, that's not. And the electron mass, right? The speed of light is all defined, and there's only one object missing in the whole SI system, which is the cesium atom. It's not an artifact, so it's not so bad, right? Because all cesium atoms are probably alike. But this will go away, for sure, right? And there's only one way to do this, and which is to replace it by the Rydberg constant. I mean, there's another way, but that would be even more exotic. Defining the electron mass, you could also do that, but then you'd have to learn how to measure 511 kiloelectron volts coherently. that's probably a bit out of the question. So yeah, this is the things that we are working on, and with that, I think my time's up, or it probably is up already for some time. And I'd like to thank my coworkers and you for the attention.
Thank you, Thomas, for this talk. Maybe the next speaker, Philip Hauke, I haven't seen him yet, but he can already start to prepare. And we have time for questions. The first one is in the first row.
Thanks for the great talk, Thomas. So there's, of course, other tests of QED. You can compare G-2 measurements to the fine structure constant measurements. So how do those connect? Is there some way to relate the tests of QED that you're doing to the tests of QED that other people are doing? And would it be meaningful if you saw something and they didn't, or vice versa?
Yeah, so this test that you're referring to in principle works in the same way. So you can use QED to calculate the G factor of the electron. It has one parameter, so that's a bit more transparent, which is the fine structure constant. And then you can make a measurement, but you have to make two measurements, right? Because there's one constant needs to be overdetermined, two measurements, which could be atomic recoils. Oops, sorry. I don't know why it does that. And the G factor of the electron. And there's also experiments with the muon G factor. Maybe you've seen this, just came out, I think, this week, right? That they finally found a puzzle there, that it didn't agree with the G factor measurement in the electron. Now it does, because they missed some theory contribution. And I think the accuracy is kind of comparable with our new 2S6P, we are actually a bit better. But one should not compare the digits. That's the wrong approach, because we don't know where the new physics lies. So maybe it lies at a point where we can't make a precise measurement. Then this unprecise measurement is much more important than the precise measurement. So it's just counting the digits, that's easy, or in other ways. If we would only look for the most accurate tests, we would only do one test. Yeah? So we should do the second, third best, and so on. So we should do as many as possible.
There's a second question.
Yeah, thanks for the nice talk. I was wondering, so when you compare these measurements to measurements of other labs, for example, are you already that precise that you have to calibrate out the gravitational redshift, the potential where the measurement is done, or is it still far more subtle than the QED effect?
We have to take it into account, but it depends where a clock is. So we are running an optical fiber all the way to Braunschweig, and I think they are at 140 meters above sea level. We are at 500. And then the gravitational redshift is on the order of a few parts 10 to the 14, and we measured 10 to minus 15. So we have to take this into account. But if what we also did in the past, we borrowed a clock, a transportable cesium fountain clock we have had. Then if it's sitting on the same potential, then it cancels out, right? So it's you cannot see this anymore. So it depends on where the clocks are and what you're comparing it with. You see the gravitational redshift only if you have two clocks and they're at different heights and you compare them. Only then, otherwise you just don't see it.
Yes, okay. Yeah, thanks.
Let us thank the speaker again and move on to the next talk.